Okay. So, I sent out that video, what was that, 2 days ago? And good answer, by the way, Justin. So, that was going over mostly what I want you to get out of that was the golden ratio. So, the golden ratio is one of the more interesting little topics in math. And really, what I want you to get out of this class as a whole is, first of all, yeah, it's skills in math. I know you wanted me to help you out with order of operations, which I'm going to send you a video for that. But yeah, I want you to get some abilities in math, but also this course, I want you to understand that math is a whole lot more than just numbers that do interesting things. Uh, Math has an intrinsic connection to how we observe our world and thus how we understand nature. And so the golden ratio is one of those ways that we have found kind of interesting patterns in nature. So the example that you gave me for the golden ratio in the human body, or really what you gave me was the golden spiral, which was great, was your fingers. So from knuckle to knuckle and then to the nail bed and so on and so forth. Yeah, if you curve your finger, then you get a golden spiral. And that's due to the ratios between the joints of your finger. So one thing that's very useful for is compacting. So if you look at your hand and make a fist, all of your fingers are curling into that spiral, and it's compacting your fist down into a smaller size. Now, other spirals can do that. You know, if we just make the spiral that most people make when they think about a spiral, uh, this is all fine and good, but it's not very efficient with its space. Okay, so the golden spiral is very efficient with its space, which is why nature uses it so much. So nautiluses and other gastropods that have well, nautilus isn't a gastropod, but you know what I mean, the spiral shaped shell. That's very useful for packing in biomatter and sort of making a more efficient use of the space that animal needs to take up. Uh, Really, that's great too because that means that the animal doesn't have to use as many resources to create that shell and to fill it. Okay, so whereas this is not a very good use of space. Another place that you see it is with plants. So if you think about a stalk of a plant, it has leaves on it, and those leaves are there to gather sunlight. That's like one of the big things that they need to do. Of course, they also aid in respiration, but we're going to ignore that for right now. The big thing that we're going to focus on is that leaves need to collect sunlight. And so, what's the best way for a plant to pack its leaves? And so, if we make a leaf here, many plants have opposite leaves. So what is the next best way for the plant to put leaves in the next layer? So this is one layer, and of course as the stalk goes up it has more and more leaves. Same thing going down, it has more and more leaves going down. Well, it can't stack another leaf right on top of this one because then it'd be blocking the sunlight from the one below it. So maybe it will pack like this, where they are 90 degrees from each other. But then again, when you get to the next layer, so if this is like the bottom layer, we'll call this one 1. And this is the next layer up. We'll call this one 2. Once you get to the next one up, if it goes 90 degrees again, well, leaf layer number 3 is going to be right on top of leaf layer number 1 and again block the sunlight. So that's not going to work. We can't do that. Okay, so what other ways can we pack leaves? Well, what if they're like a little bit opposite of each other? So instead of 90 degrees, what if we make a little bit smaller angle? So again, I'll start with layer 1. Okay, and then maybe leaves that get packed like this. Okay, well, we have now leaves that they're not quite covering each other, but they're pretty close to covering each other. And so if we add another layer here, you know, they're getting a little bit crowded, but they're not quite covering each other. Now I'm not able to draw it exactly, but this is kind of what plants do. They whirl their leaves around in a spiral, and that spiral is the golden spiral. Okay, so they use what is called a phi-th of an angle. So phi. Phi is that golden ratio. Or I think I used the wrong type of phi. There we go. So phi is 1.6180339, so on and so forth. Big, long number. In fact, this type of number is what is called an irrational number. So, rational means that it can be expressed as a ratio. Another way of saying ratio is just fraction. So if we have something like 1/2, that's a rational number. If we have something like 2, that's a rational number. Because these can be expressed as fractions. All I'd have to do to 2 is put it over 1. This number right here is an irrational number. It's like pi. You're probably familiar with pi. So pi is 3.14, so on and so forth, a lot of numbers. Big thing is that they never have a pattern to the numbers that come past that decimal, and it never ends. So these numbers don't have a pattern to them. It's seemingly random what number comes next in this series, and it never ends. Okay? So that's what we mean by irrational number. Now, using this phi-th of an angle, if we have like 1 phi between each of these layers here, then it makes that spiral, that whirl that we see in like the nautilus shells and things like that. Another place you'll see it is pine cones. I don't know if you're actually on campus at all, but there's pine trees all over Alpine. You can pick up one of those pine cones and see, like, look at it from the top, and if you look at the individual little spines of the pine cone, they make a spiral. Now count the number of spines in that spiral, and you'll get a Fibonacci number. So what is a Fibonacci number? Fibonacci number is a number in the Fibonacci sequence. That sequence is the most basic way to express the golden ratio between numbers. So it starts out 1, 1, 2, 3, 5, 8, 13, and keeps on going from there. Now, like I said in the video, with the pentagram, the sections of that pentagram could be added to each other to get the exact length of the next section. And that's exactly what's going on here. If we add 1 to itself, we get 2. So 1 plus 1 is 2. If we add 1 plus 2, we get 3. If we add 2 plus 3, we get 5. If we get 3 plus 5, we get 8. 5 plus 8 is 13, so on and so forth like that. Just like those sections of the pentagram. So this is a numerical way of expressing that golden ratio idea, that sequence. And we can actually use this to create a golden spiral ourselves with some graph paper. So resolution on this camera isn't great, so this graph paper is going to look pretty trippy. But what I'm going to do is I'm going to use these Fibonacci numbers and say that one of these little grid squares is a single number. So like 1, there's 1 right there. Okay? And for each new number, I'm going to turn 90 degrees. So the next number in the sequence is 1. So there's another 1. Next number is 2. So I'm going to go 1, 2. Again, turn 90 degrees. 1, 2, 3. Turn 90 degrees. 1, 2, 3, 4, 5. Turn 90 degrees. 1, 2, 3, 4, 5, 6, 7, 8. Again, turn 90 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So by mapping out those values of the Fibonacci sequence like that, we can see the spiral start to emerge. So again, golden ratio is one of those very interesting patterns that you see in nature, and we understand it through mathematics. Now, at this point, I want to say that there are some people out there who believe that mathematics informs nature. No, that is not the case at all. Mathematics isn't some kind of magic that people can use to conjure. Okay, it's not some kind of power in the universe. Mathematics is a purely human creation. And again, what it is, it's our way of understanding the world around us. So the most basic concept of that would be like back in the dawn of civilization. Okay. Humans would need to understand value by collecting things. So, you know, maybe you send out a hunting party, and the party comes back with a certain amount of animals. Well, you need to know how many you have. The concept of counting those animals was not always around. It was just sort of like a nebulous idea. Okay, I have killed these animals. I have two. Okay, I have a number called 2. Okay, so numbers came around through counting. And as civilization progressed, we needed to have more and more complex ways of describing value. For instance, debts. You know, if you owe a certain amount of something, well, that would be a negative number. You don't have that. That's something that you need to subtract from the current amount that you have. Okay? So again, as civilization has progressed, we've needed to have more and more complex ways of counting things. And eventually we've gotten to the point that now we're not really counting things, we're counting ideas. Okay, so math, again, is not a way, math is not informing nature. Nature informs mathematics. And that's why we look at these things like the golden spiral and the golden ratio, is because they're very interesting concepts from nature that inform our ideas of the world around us. Okay, so now for something a little bit different. And I believe Professor Kimball has already gone over this with you, and that is the pigeonhole principle, which on its surface is kind of boring. But I'll show you some interesting ways that we can use it. So the basic idea behind the pigeonhole principle is that we can organize things into different areas. Or, for the actual namesake of the principle, pigeons into pigeonholes. So if you have a pigeon coop, pigeons need to have enclosed areas for them to roost into, and those are called pigeonholes. So when you have a pigeon coop, you construct pigeonholes for the pigeons to go into and make their nests and their roosts. Okay, so right here, let's say that we have 6 pigeonholes. And if we have 6 pigeons, well, each one of them gets their own individual home. But the moment that you add another one of these pigeons into here, well, I can put this pigeon into here, that's taken up. This pigeon into here, that's taken up. This one into here. This one into here. This one into here. This one into here. But I've got this extra one, which means that it's going to have to share with another pigeon. Again, sounds kind of mundane, sounds kind of boring. Why are we even learning about this in mathematics? What does it have to do with anything? Okay, so the pigeonhole principle, again, on its face sounds kind of boring, until you start applying it to some more interesting topics. For instance, think about this. Have you ever met somebody that shares your birthday? In fact, I am willing to make a bet right now and say, yes, you have met at least one person who shares your exact birth date. Not just the same day, but the same year. Now, why am I able to say that? Why am I going to make this bet? It's because it has to have happened. So think about how many people there are in the world. Billions. Billions and billions of people. But how many possible birthdays are there? Well, if we just think about the days themselves, there's 365. So we have billions of pigeons, but only 365 roosts for them. So basically every single one of those roosts is going to be populated by lots and lots of pigeons. Meaning that your birthday, your pigeonhole, is going to be shared by lots and lots of other people. You add in years to that, well, how many years are represented by people alive right now? Let's be generous. The oldest living person was alive back in the 1800s, probably late 1800s. And then the youngest person would be right now, so 2021. Okay, well, that's at best 200 years. And again, there's billions and billions of people on the world. So again, we have far more pigeons than we have pigeonholes. However, people will tell you that because of your birthday and the stars that were aligned during your birthday, that they can tell you exactly what your future is. They can tell you what you can expect to see maybe tomorrow or the next day or the next day. They're very vague about it usually. But they'll always claim to tell you that they can tell you exactly what your future is. Well, if that's going to be your exact future because of the day that you were born, then how many other billions of people share that exact same future? It doesn't make any kind of sense. In fact, you'll probably, if you ever encounter somebody like that, one of the so-called psychics, they'll do something called a cold reading. They'll be in a group of people, an audience, and they'll say, I'm getting an M. I'm feeling M. You know, does anybody have a mother whose name started with M? Well, chances are, yeah. I mean, how many letters are there in the alphabet? Not many. How many people have a mother? Every single person on Earth. And so what are the possibilities, what are the probabilities that somebody is going to have a mother with the name starts with the letter M? Very good, just in that audience. But what's the possibility in the entire world? 100%. Okay, but they'll make that cold reading, and then if they don't get somebody's mother, oh well, maybe I'm wrong. Maybe it's grandmother. They're expanding. They're making it more and more pigeons, but the number of holes is still going to be less than the number of those pigeons. So the pigeonhole principle actually becomes pretty interesting when you realize that what it's actually saying is that things that seem like they shouldn't be able to cross over, things that seem like they would be very improbable, are actually mundane. In fact, something that I like to do when I have large classes anyway, is again with the birthdays. Find people who were born in the same month as you are. Okay, now what's the probability that somebody is going to share the same birth date as you? Very good, because of the pigeonhole principle. In fact, every single time that I've done that, at least one pair of people have shared an exact birthday. Okay, so again, math. It informs us about the world around us. And knowing about the world around us is extremely important because, well, I mean, you live in it. That should be reason enough. But also, like I was mentioning, people are going to try and fool you. They're going to try and use what seems like, logic, but is illogical. They'll tell you they have superpowers. They'll tell you all sorts of things. But really, they're just using math against you. Okay, but I think that'll do it for today. So, no class on Monday. I will see you Wednesday. Have a good one.